liftoff of the Delta II rocket with the Mars Exploration Rover.
We will launch 3 test vehicles and 2 abort test programs too. Next, we will launch another and the final demo mission. This is called the crew demo mission, and it is technically the first time the crew will be going to space. This is because the actual crewed mission starts from the operational missions, but we will be taking them as another demo mission for easier sake of understanding. Because here this is a crewed demo mission, so we have not fully certified the spacecraft. The actual test of the whole procedures of launching and landing a spacecraft with humans is still left. After launch, we will eject the abort window or the abort module, and it will eject from the spacecraft. It will land towards the atmosphere, but it won't be reused, so it will burn up. After this abort system, we will be using the next system. It is going to be a very important clearance of ejection, and it will make sure that the spacecraft will be independent, but at the same time could return and still leave an abort window. So ISRO planned a abort to orbit, abort to landing. There are multiple abort scenarios like pad abort, in-flight abort. I mentioned abort to landing and abort to orbit, and there are many more abort sequences that will be required in taking place for the spacecraft. We did the abort tests, but this will be a full abort mission, so it will have a full abort window, which means that the spacecraft can abort any time it needs. Of course, there will be some time differentials, like for example 15 hours, 12 hours, 24 hours. It depends on the spacecraft. But at the end of the day, it's an all abort system and all abort window. Another spacecraft, for example, the space shuttle, couldn't abort on pad and in flight. It could abort to orbit and abort to landing, but not do the in-flight abort or the pad abort. This would mean that the space shuttle had no ejection systems at all. So it wasn't a fully abort to scenario. Now, this will be a spacecraft that will test all these systems with crew on board. As I mentioned, it will eject its abort tower, which will be helping in pad and in-flight abort. After that, a spacecraft can use its own engines, and it's an independent body. It will take the Hohmann transfer method, which means it will burn its engines and extend its orbit at the other side. Of course, this will mean that it's an oval orbit. Now, once the oval orbit is complete, on the other side, which has the apogee, the furthest distance from Earth, we will also fire the engines to make sure the orbit is back circular. We just increase our height from 150 kilometers to, let's say, about 300 kilometers. It will depend on how long and how powerful were the engines burned. Later, we'll take usually a second Hohmann transfer method so that we can reach the intended 400 kilometer mark or the 400 kilometer altitude that we need to reach. The crew will be staying there usually for 7 days, but this can be narrowed down from 4 to 7 days. So the minimum time they have to stay is 4 days. If the systems are well going, we can be extending the mission to 7 days. After that, we have successfully tested a spacecraft. With an all abort window, we can clearly now continue for a spacecraft to make sure that it will do its next very important step. Landing, of course. But before landing, we'll do re-entry. For re-entry, we need to deorbit the spacecraft first. We are at an altitude of 400 kilometers and putting the brakes is not enough. Driving towards the atmosphere could be a choice, but not a really great one, because remember, there's high atmospheric pressure, as I told you, around the spacecraft, high vibration, and you really don't want to put your spacecraft without shielding. So you can't really shoot towards the atmosphere. You can't really just wait till the orbital will decay, because it will take 15 years for that. So we will do what's called a deorbit burn. Deorbit burn is where you take your satellite and you'll just flip it. Once you flip it, you'll fire the engines, still traveling at the same direction we were traveling earlier before the flip. What will happen is we are essentially putting the brakes. So you could imagine as your car was moving really fast, but you thought the brakes weren't enough because the brakes don't run at all. So you would put another engine in front of your car, which means that if you put your brakes, those engines will fire in front of your car and they will still stop you. And yes, it works, and it's a reverse directional thrust that will be provided. Therefore, it can deorbit the spacecraft. If we do this long enough, we'll trace a parabola. That parabola will touch one point at Earth. And you know that is a point of re-entry. Now you need to make sure that parabola is not over land, it will be over the water. It of course depends on which mission we are talking about, because some missions may want to land on land, the others just don't. For Gaganyaan, we'll be landing on the water, so the parabola will end up in the water, re-entering into the Earth's atmosphere, as I explained you, going through that very hot plasma, entering the atmosphere and enduring that high vibration in the spacecraft till we come into the lower max Q. Max Q is the maximum vibration that a spacecraft can place or use or endure during launch. When it comes to the lower max Q, it means that the pressure has decreased. And this will be, of course, the terminology for re-entry. So, we have reached lower max Q and we are in a stable descent. But we are still traveling at a very fast speed, about 1000 kilometers per second, or in short, or a very simplified number, be 7.5 meters per second. Yes, which means we travel 7.5 meters every second. That sounds fast, right? So that is why we need parachutes. Parachutes will deploy and slow down to the 7.5 second mark from an incredible 10,000 km per hour, or almost 20 meters per second. So it was a very fast speed which we use the parachutes for, so that we can survive the re-entry as well as the fast velocities while landing. Assuming that the whole mission, 7 days, and all the hours spent on this mission went fruitful, we can now say that the mission is successful. We have passed all the tests, from the test of raw materials, the vibration, the crew test, the mock-up tests, and then these flight tests, the 3 flight tests, the 2 abort tests, and the final crew demonstration test. After all these tests, we can make sure one version of a spacecraft, in fact, is capable of flying to space. This means that one version of a spacecraft is capable of flying into space. Sounds hectic? Yes, the process is a very hectic and a long procedure, usually lasting 2 to 4 years, depending on the speed and the workforce of the crew on the ground. After which we can start the operational missions of the spacecraft, and we can clarify and move on as the spacecraft can fully fly into space. And yes, there might be abort scenarios related to it. I assume and I hope that abort scenarios can be taken over by our abort systems. There are quite some failures in a spacecraft. In fact, for every 5 attempts of the largest rocket currently in build, only 2 successful, which means 3 versions of the Ariane 5 have failed. And that's why there's a really important need for abort systems, and that's why it's really important to test these abort systems. Now, these testing can be, of course, varied, and it will depend from organization to organization, from country to country. So that will mean that if one organization decides to spend some $10 million on these testing, the other one could decide to do innovative techniques and narrow it down to $7 or $5 million. So again, it will vary from place to place, but the basic systems and the basic requirements are pretty much the same. That is how you test a human spaceflight and a human man-rated system. Afterlife, or the afterlife of a spacecraft mission. If all the operation missions are completed, the contract is over, and the testing, the design, all the versions built are safely used, there's also called the afterlife of a spacecraft mission. You might think they just retire the spacecraft, right? Well, I wish if it were that easy, because there's another sort of long procedure required to retiring one spacecraft. Let's start with the first procedure. This is called the crew variation, the crew training required. So, to retire the spacecraft, we would need the crew to firstly show one type of system or to carry out one operation, and making sure that the spacecraft that will retire is still running. So not exactly as a last flight, but as a last ground mock-up system. So they'll do a testing with the ground built mock-up. After testing the mock-up, they will then restart on trying to either move for another spacecraft they want to build, another version of a spacecraft, or any other type of requirements, or the aftermath, what they will use in replacement of the spacecraft. It's another long process, and you can think of it as starting over again, like we discussed very early in this talk. So we would start over on finding out one design for the next mission. This will make sure that this will be from all properties learned from the previous mission into ensuring that any other type of manned mission can still be played after the retirement. And lastly, this third step required to doing this is called changing the museum piece, or what they want to use that same spacecraft once more. So they will usually send these to museums, but there are of course many spacecrafts built, and even if they are not reused, this would mean that some will have to go for scrap. So scrap is one part of what they could use the dead satellite for. So they can either scrap, they can send it to a museum, or they can use it as a training facility. That's right, some older spacecrafts are now built as a training facility for future astronauts to train in that type of spacecraft. These are the three applications that can be made and that can be used for after the retirement of a spacecraft, and this will usually take 6 months to 1 year so that this whole process can be applied in retiring a spacecraft. Of course, there would be some changes in policies for retirement of a spacecraft and changes in requirements for the next spacecraft that would be required in building it. Wow, that was a long process in one life of just one version of a spacecraft, which means that there could be another version that will have to go to pretty much the same process after reaching the end of its life. This is the procedure in building, training, and operating a human spaceflight mission. Thank you.